Time to get started. Thanks back there. We've got our group together. So let me start off by saying welcome everybody to the United States Quantum Information Science Summer School. It's very exciting to have you here. My name is Travis Humble. If we haven't met yet, I am the director of the Quantum Science Center. This is one of the Department of Energy's National Quantum Information Science Research Centers. It's headquartered here at Oak Ridge National Laboratory, so that's why we're hosting the school here today. But in fact, this school is sponsored by all 5 of DOE's QIS centers. And so on behalf of all of those centers, we're very excited to have you attending this school. This is an important part of our efforts to make sure that we're preparing the next generation of quantum scientists and engineers. Before we kick off our summer school agenda, which will include 2 excellent keynote presentations this morning, we have several people that would like to extend their welcome to you as well. The first of these is Dr. Gina Terasi, Associate Laboratory Director for Computing and Computational Sciences here at Oak Ridge. And I'll turn the floor over to Gina.
Good morning. On behalf of the Oak Ridge National Lab, I would like to welcome you to the second Quantum Information Science Summer School that we're hosting this year at the Oak Ridge National Lab. As we gather here today, we stand at the forefront of one of the most exciting frontiers of science and technology. We can all agree that quantum science is inherently interdisciplinary. You all represent all of the scientific domains that it takes to advance quantum science: physics, mathematics, computer science, engineering. At the Oak Ridge National Lab, all of these are core capabilities that are part of our portfolio, and we are committed to leverage our strengths in these domains to advance quantum science, to advance quantum materials, sensing, quantum networking, as well as quantum computing. So we're very excited to have you here. In order to advance any scientific domain, we need a capable and very well-trained workforce. And this is the future. You represent that future. In the next several days, you will have the opportunity to dive deeply into different quantum principles, to learn about different research topics. And this is possible because of the high caliber speakers and lecturers that we have here. So I would like to thank the broad team that made this summer school possible, and of course to the organizers, because it always takes a village. So I wish you have a fantastic experience. Make the most of it, not only in terms of the technical skills that you will develop here, but also for the network of peers and mentors that you will develop, individuals who share the same passion with you. So welcome again to the Oak Ridge National Lab, and enjoy the next several days here.
Next up, we have recorded remarks from the United States Representative Chuck Flashman. Mr. Flashman represents the 3rd District of Tennessee. This includes Oak Ridge National Laboratory and the surrounding areas. He's a major proponent for quantum science and technology, and he sent over this recording to highlight his welcome to you as well.
Good morning. I'm Congressman Chuck Flashman, and I represent Tennessee's 3rd Congressional District, including the Oak Ridge Reservation. I also have the privilege to serve as chairman of the House Appropriations Subcommittee on Energy and Water Development, which funds the Department of Energy and its system of 17 national laboratories. I want to welcome you all to beautiful East Tennessee to attend the Quantum Information Science Summer School at Oak Ridge National Laboratory. I hope you're enjoying the beautiful campus and that you're excited to participate in this unique learning experience. Advancing quantum science and technology are key priorities for the United States that are important to not only our economy, but also to our national security. To maintain our edge and advance quantum science, we need to train the next generation of the best and brightest scientists, and that's why it is so important that you're here at Oak Ridge attending the summer school. There is no better place for for you to expand your fundamental and practical knowledge of quantum concepts than Oak Ridge National Laboratory, which has a long history of reaching quantum milestones. For example, earlier this year, I organized an event in Chattanooga, Tennessee to celebrate Oak Ridge's 10 years of collaboration with EPB of Chattanooga, a utility and telecommunications company. At that event, we launched a new quantum initiative between EPB and Oak Ridge, the Collaborative for Energy Resilience and Quantum Science. This partnership has resulted in successful demonstrations of the world's finest commercially available quantum network. The work that ORNL and EPB have done together has proven the viability of quantum techniques for securely and efficiently transferring information through the nation's power grid. There are many other areas of quantum innovation happening as we speak, from designing quantum sensors capable of detecting dark matter to building never-before-seen quantum computers. The 5 DOE National QIS Research Centers responsible for organizing this event are at the forefront of these events. Under the oversight of these centers, institutions across the country are sharing resources and expertise to usher in a new quantum age. I'm supporting these efforts through my fiscal 25 energy and water appropriations bill, and I'm looking forward to seeing great things. We have seen tremendous advantages in the world of quantum in just the past few years, so all of you have big shoes to fill. I encourage you to take advantage of this opportunity to learn from our world-class scientists at Oak Ridge and practice the skills you will need to become a successful member of the quantum workforce. While you're here, I encourage you to ask a lot of questions, broaden your horizons, and leave with an excitement that the work you're doing will make a difference. I am confident that the time you're investing here will set the stage for your future careers. I hope you enjoy your time in East Tennessee, and I look forward to seeing great things that will come from this group.
As Representative Flashman just pointed out, the 5 centers representing the summer school today are actually part of the National Quantum Initiative, and in particular, part of the Department of Energy's efforts to stand up focal points for fostering research and innovation in science and technology. We're next hear from Dr. Jaron Sussit, the Associate Director for the Advanced Scientific Computing Research Program Office within Department of Energy. Jaron, I'll turn the floor over to you.
Thank you, Travis, and hopefully everyone can hear me. I am very, very happy to welcome the students, lecturers, and special guests to the U.S. Quantum Information Science Summer School, and I'm sorry that I cannot be there. As you may know, the DOE Office of Science is the nation's largest supporter of physical sciences in the United States, and our portfolio includes the vast areas of science and in the United States, spanning from biological and environmental research to chemistry and materials. And of course, quantum information science is a major initiative within the Office of Science. Ensuring American leadership in this fast-growing field might seem daunting, but the National Quantum Initiative provides us with a blueprint. And DOE is one of the leading agencies in the National Quantum Initiative. And one of our major contributions are the 5 national QIS research centers. These centers address grand scientific and technological challenges that would not be possible to tackle without a consolidated approach. Each center has a tremendous team of highly skilled scientists and engineers representing universities, industry, and national labs. Many of these impressive individuals are with us today, with you there today. Unfortunately, I cannot be there, but you will soon have the opportunity to learn from them through invited lectures and other hands-on activities. The second installment of the U.S. QIS Summer School is hosted by the Quantum Science Center that Travis is leading, and will highlight some of the DOE's unique capabilities in high-performance computing, nanofabrication, and neutron science. All of these techniques are critical to advanced quantum research. Pursuing research results is one thing. It's of course very important, but we in DOE, we also understand the importance of people that make it all happen. Therefore, we do prioritize our efforts to recruit and train the best and brightest future scientists. We are so glad you are joining us in the next couple of weeks. Your selection and participation in the school represents your hard work and achievements to date, and we hope to help you to grow further into your careers as confident scientists. We also invite you to apply for additional opportunities sponsored by DOE and the QIS research centers. In fact, I cannot be there today because I'm here in the Computational Science Graduate Fellowship Program Review, another unique opportunity offered by DOE, specifically sponsored by the program that I represent, Advanced Scientific Computing Research. Again, I thank you all for joining us today, and I wish you the best with your studies and your career paths moving forward. Thank you.
On behalf of Oscar's research program, I'd like to welcome all of you. I have a few minutes now to try and say something inspiring, so that's my job. We are really, really proud of all of the accomplishments of the community that we have around computational science, around computer science, around applied mathematics, and around high-performance computing for the scientific enterprise. Here at Oak Ridge, we have Frontier, which was the nation's first exascale supercomputer. It was fielded by our program. And it comes at a pivotal time for computing, for science, and for the nation. We have reached exascale through a combination of innovation in hardware, in system software, and in applications and algorithms. All of those things had to come together in order to make that possible. And now that we have achieved that tremendous milestone, we stand at an inflection point in computing. Moore's law is slowing. We are seeing an increase in heterogeneity, which makes systems more complicated to produce and to use. We are seeing a tremendous advance in artificial intelligence and in data-driven algorithms. And at the same time, and I suppose if you read the news, you understand that all of that requires a lot of power. And so we are really, really focused on energy efficiency. Energy efficiency, the primacy of that requirement has become increasingly apparent as we move forward. Luckily, we also have a number of new computing paradigms and technologies which are increasing in their level of maturity. These include, of course, quantum computing, networking, and sensing. And all of you will hear and learn a lot more about those areas, although I'm sure you already know quite a bit. But it's more than that. Many other computing paradigms in which people are very interested, things like photonics and spintronics, superconducting logic, and so on, are also quantum technologies. Quantum technologies pervade the future spectrum of advanced computing, and it comes right when we need it. Of course, there are other trends as well. The growing complexity of software, scientific software, but all software more generally, and the spread of where we think of advanced computing as residing, from being just in a data center to being everywhere. The data center, the edge, everywhere in between. We need advanced computing just about everywhere in order to advance our scientific enterprise. But as I said, all this has to come with an increase in energy efficiency. We have to not only create new capabilities, but we have to be able to run them. We have to be able to use them effectively. And quantum phenomenon sit at as the kind of keystone principle underlying all of this kind of technology. But more than that, even though all of what I said is true, it's also quite challenging because there are lots and lots of unknowns in all of these places. From the computer science side, we have major unknowns in the theories of computational complexity. And of course, adding on top of that what we know about quantum algorithms doesn't necessarily make that any simpler. Quantum technologies sit on this boundary between what we know about computation, what we know about the theory of information, what we know about the theory of thermodynamics, and what we know about the theories of fundamental science. And so here, you have to consider all of these different factors. And you have to consider them in a very coupled way. You'll hear about quantum computing. You'll hear about all of the challenges that people have with the pursuit of quantum error correction. And you'll probably realize that thermodynamically, quantum error correction is a cooling procedure. You have to think about these connections. You also have to think about the fact that when people are talking about creating quantum computers that have millions of qubits, they also start talking about requiring tens or hundreds of megawatts of power, which in and of itself is going to be quite a challenge. So we have to think about the energy efficiency of all of these different things. But we also have to think about the fact that the science here requires a lot of further exploration. And the next generation of scientists, and I think I'm staring at a lot of them right now, are going to be the ones to tackle these challenges. I was reminded the other day when I was looking at the Wikipedia page on quantum thermodynamics that it wasn't until about 2018 that there still were major open questions about whether quite straightforward, simple systems to describe violated the second law of thermodynamics. 2018 wasn't ancient history. And I think we all have to think about this quite carefully. So you're going to hear from world-class speakers here, and I think you should learn from them an awful lot. And you're going to tackle the fundamental challenges of quantum mechanics combined with the fundamental challenges of computation. You're going to have to put all those things together. I was pleased to see on the agenda that John Preskill will be giving a keynote later. It reminded me of a fun paper I saw last year that he had written on emergent quantum mechanics from some classical lattice systems. It was a year ago, don't ask me about the details. But it reminded me of the following thing. Quantum mechanics has a really strangely broad universality in physics. It's everywhere. It's in all sorts of places. We don't really know why exactly, but it is. And it pervades all of the different technology areas which are so critical to the future of computing. So we have all of you here to study quantum mechanics. It has a universal applicability. We don't know exactly where that universal applicability starts, and we don't know exactly where it ends, but we do know that it's going to be essential for us to meet the future computing needs of our scientific enterprise and of our nation. So with that, I wish all of you luck. I hope you all have a really good time, and I hope you invent the next generation of computing. Thank you.
Next up will be Dr. Sean Gleason, the director of the Security and Science Initiative here at Oak Ridge National Laboratory, which examines how quantum technologies can impact our mission for energy security. Sean.
Good morning. welcome to Oak Ridge National Laboratory. It's terrific to have you all here. I hope you have an amazing couple of weeks enjoying the lab and the surrounding area. And as Gina said, getting to know each other and expanding your professional and social network. So happy to have you all here. I get the privilege of working in a pretty cool job where I get to play in the fields of artificial intelligence, a little bit in high performance computing, and in quantum science and technology. And those fields are very highly interconnected, as many as of you know. And one of my jobs is to figure out how some of the scientific discoveries that we're making in those fields, including quantum, can translate into national security applications and vice versa, how there's national security applications that are driving quantum S&T development and how those can benefit the more open science community. So it's a fun job that I have, and I'm honored to be able to say a few words to you all this morning. As has been said, the opportunity to leverage quantum physics to really advance the state of science in the world is huge. Quantum has the opportunity to help us see the world differently, sense the world in a completely new way, to transmit and share that information more efficiently and more securely. And also, when you talk about quantum computing, as has been said, some of the most challenging problems that we know we cannot solve, even with the largest supercomputers on the planet today, quantum computers have the potential to solve those problems. Now, will that be 5 years from now, 10 years from now? We don't know, but if you guys are really good, maybe it'll be 3 years from now. So there's motivation for you to help us solve some of these big problems. So one of the things I wanted to mention is that ORNL, we have the goal to create a regional innovation ecosystem for quantum. And when I say regional, we're talking about East Tennessee, Tennessee, and the Southeastern United States. So we want to advance quantum science technology to impact this region. And if this region, being the Southeast, can be a model, then it can extend across the US and across the world. But over the next decade, we would like to create this regional quantum science innovation ecosystem. We can't do this on our own. We need partnerships with other labs. We need partnerships with universities, from which many of you are coming from. And we need industry partnerships are critical to move the quantum science discoveries and innovations that you all come up with into practical application with industry partners. And another couple of examples of those are in the energy space. You heard about the Electric Power Board in Chattanooga. You're going to hear from Jim Ingram next, who's going to do a little bit of an intro as well. We're partnering with them. We're partnering with the Tennessee Valley Authority to try to figure out how do we bring quantum science and technology, as Travis said, into the energy industry and have an impact over the next decade. So it's a very exciting field to live in and to be working in. And the goals, there's multiple goals for this innovation ecosystem. One, we want to advance science. We want to break through boundaries or barriers and advance quantum information science. We want to create the next generation workforce, as has been said. I think we're looking at a big chunk of that right now. And we want to create economic opportunity. We truly believe that over the next decade and even sooner, quantum can make a huge economic impact for the good for this nation and for the world. So I just want to encourage you to enjoy the next couple of weeks. Thank you for coming, and I appreciate the opportunity to talk with you all this morning.
Okay, so our next speaker, Mr. Jim Ingram, is the Vice President for Strategic Research at EPB. And I think you've heard people say those three letters now a couple times. I'm going to let Jim explain exactly what this is, but it is a great example of what Sean was hinting at, of how quantum technology is already making a difference in the world around us. So with that, I'll hand it off to Jim.
I use the test tip. Nope. I've got a big mouth. Can you all hear me? Okay. Well, Welcome to the community, the smartest people in the world. That's why I'm up here from my company, EDB, in Chattanooga, Tennessee. We're okay. Sorry about that. I'd like to walk around if that's okay. Yeah. Okay, well, there goes half of what I was going to say because it's being recorded. So I'll cut this in half. Let's talk in half. What I want to talk to you today is about why my company is interested in quantum technology. We are a municipal electric utility. We're in the broadband business. We have built a fiber to the home network to past every home and business in metropolitan Chattanooga. We serve about 350,000 people in metropolitan Chattanooga. We just upgraded that network to the Nokia PON technology. We're the only city in America offering 25 gigabit symmetrical internet today. We have what we believe to be the most advanced automated electric distribution system you'll find anywhere in our country today. We're here working with the folks at Oak Ridge National Laboratory because that value has a time limit to it. Does anybody know the phrase, I feel the need for speed? That's from Top Gun, right? Well, these technologies, there is a need for speed to stay ahead. We maintain our brand with state-of-the-art technology and platinum customer service. To do that, we have to understand these technologies as they evolve. Therefore, Vision 2035, our look 15 years into the future today, that's 10 years into the future almost. So I'm in the electric business. I'm in the broadband business. It took, look at the slope of that line on the left. It took decades for everybody in our country to get access to electricity and telephone service. Look at the slope of the line on the right. Cell phones, computers, the internet, less than 15 years. I like metaphors. This is the Vatican in Rome. Anybody from Italy? Okay. So you know the Vatican. So see the cell phone down there? This is when the Pope comes out every year and speaks to the Catholic Christian world. Now, what happened in 2007? This little device came out, right? The iPhone. 6 years after that, what happened? That's how fast this technology evolves into the marketplace. And in order to stay ahead to serve people, you have to understand it. You have to be not just a part of buying it, you have to be the part of developing it. You may not know, but in your iPhone, there are 16 technologies. How many of them did Steve Jobs invent? None. Guess where they're invented? Right here at the national laboratories. Does anybody ever touch your iPhone, the screen? The touch screen, that technology was invented right here at Oak Ridge National Laboratory. That's why we're working with Oak Ridge. The internet started out as printed text and still photography. Today, streaming video, uncompressed sound. We believe it will become artificial intelligence integrated with augmented and virtual reality and automation. We believe that the quantum computing and quantum networks will drive that third generation internet. I'm in the energy business. Just had a couple of conversations this morning about some of the challenges we're facing in the energy industry. It used to be you built big power plants and you sold electricity as a commodity. We're making huge investments today in Chattanooga, and everybody in our industry is, in distributed energy resources. But how do we control and manage those distributed energy resources in the most efficient and effective way? We believe these technologies will help us to do that. This is one of our customer service representatives on the left. EPB since 2016 has been #1 with JD Power in customer service in the electric utility business. And it's these ladies that are a big part of the reason for why we're #1. We believe that that job will look something like what is on the left in the next 10 years. These technologies will drive our ability to solve problems for customers much faster. But we don't believe it will replace people. We believe it just will make people more productive. see the virtual reality world on the right up here. We believe it will evolve to something looking closer to what is on the left here. This is a virtual reality environment. If they give you a chance here at Oak Ridge, you ought to go over and see some of the virtual reality capabilities they have here at the lab. They're pretty amazing. Quantum computing is coming to life. There's no doubt about it. In fact, it's coming to life not just at the national labs at our universities, but in the commercial market space. This is the IonQ trapped ion microprocessor. This is the one that works at room temperature. We believe that this is the most likely technology right now to proliferate, but it is kind of like the Tandy computers I used to see at the mall when I was a young man. They're very early, they're clunky, as you know, to operate right now. But we believe integrating them with the supercomputing capabilities here at Oak Ridge National Laboratory, there are productivity advantages you can gain in the next 5 to 10 years. This is the photon source that was developed by Dr. Duncan Earl. He's the chief scientist for our network in Chattanooga. He is a University of Tennessee trained physicist. He worked here at Oak Ridge for 18 years. We started working with Oak Ridge in 2016. We had a 13-kilometer fiber network where we were learning to tune our fiber system to pass entangled photons across that point-to-point network. As a result of that research, which was award-winning, we won an R&D 100 award, Oak Ridge did and Cubatech did, we were a part of it. We made the decision to build the EPB quantum network. It is a 4-qubit, 7-kilometer loop architecture that exists in our community today. It is the result of a 10-year working relationship between Oak Ridge and EPB. You heard Congressman Flashman talk about that. You've heard Dr. Gleason talk about that. You'll hear probably some more about that. And in fact, come see us. We'd love to show you what we're doing if you have the time. But that network exists in Chattanooga today. This is a picture of it. And it is operational and functional. We are serving several federal agencies, several research universities, and a lot of small quantum companies are coming to use our system to manage the productivity of their technology to prove its revenue potential and readiness for market. There's a huge business opportunity associated with this evolving artificial intelligence and quantum technology. Think of that computing technology, cellular technology, internet technology, what that has meant to the global economy. This is from the McKinsey Quantum Monitor on artificial intelligence. Google it, it's free, look it up. Artificial intelligence market is almost $8 trillion. And it's growing. And here's the thing, most of our industry groups have not adopted AI yet. The biggest thing you hear about is ChatGPT, right? So they're very expensive to develop. A lot of them are based on open source data. The use cases are limited, but there are not a lot of use cases in my business, in energy, in communications. But our country right now is far and away the leader in the world in developing those use cases for artificial intelligence. We want to maintain that lead. In the quantum space, this is the McKinsey Quantum Monitor. Again, the report's available online. $1 to $2 trillion for the equipment, communications equipment, computing, sensing. These are the use cases that are going to generate the productivity improvements quickest. Notice the 2 red arrows, energy and communications. That's where we are. But in my community, we have finance, we have insurance, we have advanced manufacturing, we have logistics. We are looking at how, in the early days of these technologies, we can find practical applications for them to build on. That's why we're interested in investing and building the technology. And by 2035, we hope in Chattanooga to be ready to build a quantum-based internet based on qubits. We will have a distributed electric distribution system that will be controlled by these artificial intelligence algorithms that are constantly being fed by quantum simulations in quantum and supercomputing. That'll give us quantum age living for our customers, customer service, and control. In Haiyai, I don't know if I'm saying that correctly, but the Chinese have built a quantum city. This is a picture of it. That's the reality of it in 2022 versus 2019 when we were planning to build our network. There is a national security and economic competitive reason for us all to be in this. Our community is determined to be a part of that solution. Going forward into the future, we hope in the next 10 years that the largest companies in our community, including the Tennessee Valley Authority, that we will be streaming our data into an infrastructure that is based on the EPB quantum network, our advanced data and control system integrated with the quantum computing and supercomputing here at Oak Ridge National Laboratory that creates a network of generative AI libraries of proprietary, not open source data that can be used in a safe environment to develop these applications. We're working closely toward that today. That's what we're up to. Come see us. We'd love to see you down in Chattanooga. Thank you.